Okay, last section in chapter 1, which is review, is on exponential functions and logarithms. So let's take a look at what we got. Okay, so first are just the basic properties of exponents that you kind of have to review every time you take a math class. And which kind of go ahead and show you some examples, right? So the first kind of guy, 3 to the 0 power equals what? Anything to the 0 power is 1 except 0. Okay. Secondly, there's kind of, if you have like bases that are multiplied together, so let's say 2 cubed times 2 to the 4th, you add the exponents. So you'll have 2 to the 7th. Okay. If you have like bases and you're dividing, so let's say I have 2 cubed over 2 to the 4th, you subtract the exponents. And you can go in either way. You can bring the bottom one up, in which case you get 2 to the 3 minus 4. Which is 2 to the negative 1. Or you can bring the top one down. So you get 1 all over 2 to the 4 minus 3, which would be 1 all over 2 to the 1. Okay. So from there you can kind of see there's some negative exponent rules. So if you have like 5 to the negative 2, you could rewrite that as 1 all over 5 squared, which is 1 over 25. Stuff like that. Okay. Power. So when do I multiply exponents? That's when you have kind of a product raised to a power. So maybe you have 3x to the 4th raised to the 3rd power. Then you're going to be kind of multiplying the exponents. You pretend there's a 1 on the 3, so 3 to the 1, 3 to the 1, and you go 3 times 1, so 3, and then x to the 4 times 3 is 12. So that's when you multiply the exponents. You can do more complicated versions of this. Let's say negative 3x to the 4th y cubed all over z to the negative 1. And raise that to the negative 3rd power. No, negative 2nd power. Okay. So, right. Usually what I'll do is kind of separate off the negative 1 and write it like that. You may have learned it different. Whatever you do is fine. And then I can multiply the exponents. You could flip it and then change the sign of the outer exponent. I'm just going to multiply the exponents. So the negative 1, well, sure, let's flip it. Okay. To get rid of that negative 2 on the outside, you can just flip the inside. So you get z to the negative 1 all over negative 1, 3x to the 4th y cubed with a positive 2 on the outside. So you can do that. Then I can kind of multiply the exponents. So on the negative 1, there's an exponent of 1. On the 3, there's an exponent of 1. So I'll have z to the negative 2 all over negative 1 to the 2th power, then 3 to the 2, x to the 8, y to the 6. So I'm multiplying exponents. You want to get rid of any parentheses and negative exponents. Okay, so first I'm going to move this guy downstairs. That will change the sign of the exponent and leave a placeholder of 1. Down below, negative 1 squared is just positive 1. So I don't have to even worry about that. And then 3 squared is 9. And then have x to the 8th, y to the 6th, times z to the positive 2. Okay, okay, so they can be really challenging. If you need some help with that, you can stop by my office hours. They have free tutoring, I think, online right this semester. You can, hopefully they've emailed you. You can ask me and I'll funnel through the millions of emails they've sent me and try to find it. But you can always stop by my office during WebEx hours on WebEx. Or you can just pick up, probably go online and find like an algebra review app or something like that. Okay, some examples. Another kind of problem you may encounter are fractional exponents, right? So this is the same as 25 cubed to the 1/2, but you can also write it as 25 to the 1/2 cubed, right? And that allows us to kind of do the computations in our head. 25 to the 1/2 is 5. Cubed is 125. So you don't need a calculator, in other words, to do some of these. All right, I think that's kind of, so if you need some help, my notebook is flipping out on me because I've been using the same notes for the last 6 sections. So let me add another page here. And then I'm going to have to screw around with the, okay, I think that does it. Oops. It was just, the page was starting to flip out on me. Okay. And I could white pen. All right, here we go. Sketching these guys, what do they look like? They look like ramps, right? So the exponential growth, you hear that sometimes they talk about the virus, the coronavirus and stuff like that. Exponential growth, so this is y equals a to the x, where a is greater than 1. Okay? And then, of course, if a is in between 0 and 1, we have the rotated version, exponential decay. Or if you'd rather a to the negative x, again, a is greater than 1. I don't know, so there's that. What's the domain here? The domain is all real numbers, negative infinity to infinity. The range, you can see it's going from 0, not including 0. Okay, so there's no way to make 5, there's no x value you can put in here to make 5 to the x equals 0. Okay, that just will never work. So 0 is not in the range, is what I'm trying to say. And the y-intercept is when x is 0, so the y-intercept is 0. You plug 0 into this thing, 5 to the 0 is 1, so 1. And it's 1 to 1, so this thing is invertible. It passes the horizontal line test. Okay. So we can use translations to graph these guys if that's what you're being forced to do. Try not to rely too much on the calculators. You don't want to be dependent on your computer overlords, I would call them. Try to figure out how to do things on your own to an extent. You know, you don't want to hobble yourself. Like you can imagine me using the oven versus my next door neighbor using a microwave. You know, the microwave person is going to get stuff done a lot quicker. So computer is a powerful tool. You want to use it. Okay. So anyways, let's graph y equals 3 to the x, and then we'll just use translations to get y equals 3 to the x minus 1. Okay. So x and y. I'll try -2, -1, 0, 1, 2. 3 to the -2 is 1/9. 3 to the -1 is 1/3. This is 1, this is 3, this is 9. Let's get these points going. 1, 2, 1, 2. And then 1, 2, 3, 4, 5, 6, 7, 8, 9. Whoops, I went too far. Let's put it in yellow. So -2 is 1/9. -1 is getting a little higher. 0, 1. Oh man, really? Stupid button on this pen. That's the one drawback of the system I'm using. This pen is just 1, 3, and then 2, 9. Connect the dots. There we go. Sort of. All right, so that's our first graph. Y equals 3 to the x. Our second graph, let's put that in red. Okay, we just shift it to the right by 1, right? So this is f of x minus 1. That means go right 1. So I take each one of these points and shift them over by 1, and then connect those dots. I'm going to need another tick mark on my axis. Finally take this guy over. 1, and draw that. Cheat a little there. So y equals 3 to the x minus 1. Okay, no big deal. So the exponential function has an inverse, and that is the logarithm. In particular, we'll work with the natural log that has base e. Okay, so that e is like 2.71 or 17 or something, that big transcendental number. It's like pi. So usually, what is the definition of the log in general? So log base b of x, y equals log base b of x is the same thing as saying b to the y equals x. Okay? So if you have log base e of x, which we're going to call the natural log of x, just like log base 10, you call log, just plain old log of x. So if that's the case, then there's some simple values we should be able to figure out, just like, let me not get ahead of myself. So what is the ln of 1? These are things that you should know off the top of your head, right? Okay, using the definition, this is log base e of 1, and so it's asking e to what power equals 1? Well, 0. So ln of 1 is 0. Let's do another. ln of e. Log base e of e. So it's asking e to what power is equal to e? Well, that's just 1. Okay. So these two you should know off the top of your head. ln of 1 is 0. ln of e is 1. Okay. Okay. Sketching these things. How do I sketch them? Usually you draw the exponential version and then just rotate it around the line y equals x for its inverse. Okay. So sketching log. So y equals e to the x will look like this. And then its inverse, to get the inverse, you just rotate it about the line y equals x, which is this line here. And I'll put the logarithm in yellow. And so it looks like this. Okay. What are some characteristics of the natural log? Well, the domain is the range of the exponentials, so that would go from 0 to infinity. The range is the domain of the exponentials, so negative infinity to infinity. We have an x-intercept this time. That's where y is equal to 0, and x will be 1. And then it also, too, is 1 to 1. Okay. Graphing this guy, you can do translations again. So example, and this will lead into the next problem. Y equals ln of, let's say, e squared times x. Okay? So you can think of it as a horizontal smush. Okay. But there's another way to do it. You could say, well, this is the same as ln of e squared plus ln of x. Okay? And then ln of e squared, e to what power is e squared? Well, that's 2. In other words, it's just a shift of ln of x up by 2. So you can draw ln of x already. Maybe not perfectly, but you can get an idea of it. Looks like that. And then you just take that thing and shift all of its points up 2. So 1, 2. 1, 2, stuff like that. 1, 2, 1, 2, 1, 2. And then we'll have a picture, something like this. Okay, so what did I just do there? Well, that was one of the properties of the logs that you probably learned in previous classes. So what are some properties of logs? There's conditions. You can read the conditions in the book. ln of x times y is the same as the ln of x plus the ln of y. And that's what I did in the previous example. Okay? I just split up the guts of the log and turned it, the log of a product into the sum of the logs. Okay. You could do the quotient rule as well. ln of x over y equals the ln of x minus the ln of y. And then the power rule, ln of x to the p is p ln x. Okay, so an example of the power rule, say you have ln of e cubed. Well, that's just 3 ln of e. And then ln of e, we know from above, e to what power is e? Well, that's just 1, so this is 3 times 1, which is just 3. Okay. In other words, e, if you look at ln of e cubed, you're asking e to what power is e cubed? And that's just 3, so yeah, that works. Okay, so in college algebra and pre-calculus, you learn how to expand and condense these things. We'll want to do that for the homework. So an example, ln of x times the square root of x squared plus 5. Okay, so expand. First I'm going to do the first law or property, which maybe they call that the product rule for logarithms. So ln of x plus ln of the square root of x squared plus 5, but I want to write the square root as a fractional exponent. Okay. So you can always rewrite, like the cube root of x is the same as x to the 1/3. The fifth root of x squared is the same as x to the 2/5. So we kind of see the pattern of how that works. Okay. Now I can use a power rule and rewrite this as ln of x plus, bring the 1/2 in front. This 1/2, I can bring that out in front. 1/2 ln of x squared plus 5. And then I'm done. Okay, I can't factor that x squared plus 5 into products, so I'm kind of done. So if you can expand, you also need to be able to condense. A harder one. Third, 2 ln of x plus 3 plus ln x minus ln of x squared minus 1. Okay. I'm going to work on the inside first. Okay, so it'd be 1/3. I can bring the 2 inside this logarithm. So I have x plus 3 squared. Then I could use the product rule on the first 2 logarithms. So I just do one thing at a time. You can do it all at once if you get really good at it. So I'll have x times x plus 3 squared inside that log minus ln of x squared minus 1. Then you could use quotient rule on those 2. You get ln of x times x plus 3 squared over x squared minus 1. And then finally, power rule. Bring that up inside here. And you get ln of the cube root of all this jazz. Okay. Okay. Solving these equations. So solving. There's a bunch of different kinds of these guys. Usually you just kind of you exponentiate or you take the logarithm on both sides. But there's other kind of ways to do it, just using the kind of equating the exponents and stuff like that. So let's look at a couple of these. So first, the exponential version. Exponential equations. So an example, maybe we have something like 5 to the x minus 2 equals 25, right? So if you get the same base on each side, you can just equate the exponents. So you can rewrite 25 as 5 squared, and then you could say, well, that means x minus 2 is equal to 2, so x must be equal to 4. When you don't have the like bases on each side, you got to take logs on both sides. So take the log of both sides. So for example, 3e to the x minus 2 equals, I don't know, let's say 11. Okay. No, let's make that something nice, 14. I don't know why I thought that would be nice, but it's not. Let's look at it though. Okay, so move the 2 over. That'll give me 16. Divide by 3. So you want to isolate the exponential, and then take the log on both sides. Okay. So ln of e to the x, ln of 16/3. ln of e to the x is just x. The ln and the e are natural enemies, right? So they kind of cancel. If you don't like that, you can do the power rule and say this is x ln e. ln of e is just 1, so x equals ln of 16/3. Okay. This can be a lot more complicated. So maybe something like solve for x, where you have 3 all over 1 minus e to the negative 2x equals, I don't know, 7. Cross multiply, so 3 equals 7 times 1 minus e to the negative 2x. And you want to isolate the exponential term. Okay, so let's distribute. I'm going to move the 7 over, so we got negative 4. Divide both sides by negative 7. Exponentiate or logarithms on both sides. Power rule, or you could think of the ln and the exponential cancel each other. And then divide both sides by negative 2. Okay. Okay. These kind of equations come up in modeling. It's called a logistic equation. So you use it in modeling disease as well. Okay. You also use it in neural networks, determining when a neuron is going to fire in your code. Okay. All right. Find domain type. Sorry, we haven't done logarithms. Log equations. Usually you'll just end up exponentiating both sides or using the definition of logs. So use definition of logs or exponentiate both sides. The problem with these is you have to check your solutions. Okay, so let's take a look at an example. So log base 3 of x minus 2 equals 1. Okay, so you could use the definition of logs here. 3 to the 1 equals x minus 2. So x is going to be equal to 5. You got to check it. Okay, so put 5 into here. Log base 3 of 5 minus 2, and you got to make sure that it's the same as the right-hand side. Log base 3 of 3. So 3 to what power equals 3? Well, that's 1. It works. So the solution is 5. Another example, log base 3 of x plus log base 3 of x minus 1 equals, I don't know, I gotta make this so it works out. I think minus 6 will work. So if I get a minus 6 over there, minus 6, I can use plus 6. So I need it to be 6 eventually. So let's go log base 6. Okay. And put, I'm going to put over here, log base 6 of 6. I don't know why I needed to go through all that rigmarole, but we could use base 3. It won't matter. Or just log base 10, I guess. Well, we'll see. I may have to change the problem. Okay. So first, I'm going to use the log properties of logs here. So I get log of x times x minus 1 equals log of 6. And then I can equate the insides of the logs, just like above I equated the exponential. So x times x minus 1 equals 6. And then it's just a quadratic. Bring the 6 to the other side. And so x minus 3, x plus 2 is 0. And then x is 3 and negative 2. And then I got to check both of them, right, in the original equation before I messed around with it. So x equals 3. I have log of 3 plus log of 3 minus 1, which is 2, equals log of 6. Log of 3 plus log of 2. You can use properties of logs to make that log 6, and that is the same as log 6. So that works. Try negative 2. Log of, oh, that's not going to work, right? So as soon as you get a negative inside of a log like that, you're out of luck. Logs, the insides of logs have to be greater than 0. Okay, so this is bad news. You can stop. That means this is not a solution, and our only solution is 3. Okay. One more where we kind of have to exponentiate. So let's say I have ln of 2x minus 3 plus 5 is 0, or maybe minus 5. Okay, so I'll get the 5 on the other side, isolate the logarithm, and then you can exponentiate both sides. Okay. On the left-hand side, the e and the ln kind of cancel each other out. Okay, that goes back to the cancellation equations, right? So if you have f of x and its inverse, f of f inverse always equals x. So if your f of x is e to the x, and f inverse of x is ln of x, what is f of f inverse of x? Well, that's e to the ln of x. And because they are inverses of each other, that has to equal x. Okay? So on the left-hand side, those parts will sort of cancel, and you get 2x minus 3 equals e to the 5th. And then you could solve for x. I'm dividing by 2 finally. And then we have to check ln of e to the 5th plus 3 over 2 times 2 minus 3 minus 5 better be the same as 0. Ln of these 2's cancel, e to the 5th plus 3 minus 3 0. So that'll be ln of e to the 5th minus 5. Yeah, that works. So 5 minus 5 is in fact 0. So circle that, that's our solution. I think they have, let's maybe look at one on WebAssign. They have like some domain type problems that are kind of weird. Okay, where's my editor? 1.6. There's a lot of homework, so get in there and get it done. These look kind of weird. Maybe I should do one of those. I don't know. Let me do one of the domain type problems first, then I'll go back. Oh, and the absolute value, ln of absolute value of x. Every once in a while, this issue comes up. Ln of x squared. What is that? Does that equal 2 ln of x? No, not quite. Right. So on the left-hand side, the domain is actually everything except 0. And the domain on the other side is different. Okay, so they're not the same thing. So how do I get around that issue? And you can get around the issue by using some absolute values. Okay, and then that will have the same domain as this. Okay, so what then is this thing? What does it look like? The ln of absolute value of x. Well, it's going to be plus or minus something, right? So one thing that sometimes we have to do is rewrite absolute values in terms of the piecewise definition. Okay, so y equaling ln of the absolute value of x will equal ln of negative x if x is less than 0, and then ln of positive x if x is greater than 0. We can't use 0 because it wouldn't work in this. So negative x, ln of negative x is just the rotation of the ln of x, which looks like this, about the line y, about the y-axis, right? So if I rotate that thing about the y-axis, I'll draw it now in yellow, I get this thing here. Okay. So both of those together is the y equals ln of absolute value of x. Okay, so this piecewise definition for the absolute value becomes kind of important sometimes, and hopefully you've seen it before. If not, there it is. Okay, so it's another way of writing absolute value of x. What else do we have? Find the inverse of that thing. It's kind of like solving. Expand, condense, condense. It's kind of an application. Let's take logs. And I don't know why that one's in there. Oh, that's just a simple one. Which one should I do? This one looks like a nightmare. Let's try this one. Okay. So first I want to find the inverse of this thing. And scroll down a bit. So I have f of x equals 4 plus the ln of 2x. Okay, and I want to find the inverse function for it. Ooh. All right, so I'll say x is equal to 4 plus ln of 2y, and I want to solve for y. So I'm going to move the 4 to the other side. Ln of 2y equals x minus 4. Oh, this ain't so bad. And then you just, e to the x minus 4 using the definition of the natural log equals 2y. And so y equals e to the x minus 4 over 2. And if you got to, you can use Desmos to kind of figure out where that is or how to graph it. You shouldn't have to too much. It's going to be a shifted version of this guy up 4. So 1, 2, 3, 4. So it's a new kind of origin will be sitting right there. And then we need to rotate it about the line y equals x. So it'll look like this. Okay. All right. Let's see. Is there anything else that looks nightmarish? There were some ones I was like, I don't know about that one. It's graphing. Find the domain of this thing. So the domain of one of those logistic looking things. Let's work with that a little bit. 1 over 8 minus e to the x. So to find the domain, it's all real numbers except where the denominator is equal to 0. So literally, it's everything except the x's that make that true. So you solve this equation, e to the x equals 8. Take the natural log on both sides. So I have x equals ln of 8, and it's the only bad place. So the domain will be everything except that. Okay. It's just a shift. There's some weird ones up here. 1/4 to the x minus 2 equals 64. That's just one of those ones where you have to kind of rewrite it with like bases on both sides. So 1/4 is the same as 4 to the negative 1. That's an x minus 2 if you can't read it. 64 is the same as 4 cubed. Okay. And then you can, multiply out those exponents. So 4 to the, but you have to distribute. So 4 to the negative x plus 2 equals 4 cubed. So negative x plus 2 is 3. And then what do we have? X equals, bring the x over and subtract the 3, minus 1. We got to check that. Was that a logarithmic equation? No. Okay, we're good. Anything else annoying? Terribly annoying. What was that inverse guy? Just checking to see if they're inverses. Expand, condense, solving. Maybe this guy. Solve the equation accurate to 3 decimal places. Let's try that, and then we'll call it quits. So what we got? 1 plus 0.9 all over 365 to the 365t. It's an expression you would see in accounting. Okay, that's, what is that? The compound interest formula. All right, so how do I solve it? It's basically what it's coming down to. Take ln on both sides, or yeah, sure, ln here. So I'd have 365t, so you can bring down this exponent and put it in front, times the ln of 1 plus, that thing. This doesn't look very hard now anymore. Then divide by anything that's not t, so you're dividing by 365 ln of 1 plus 0.9 over 365. This is really silly. And then you'll have t equals, of course, ln 8 all over 365 ln of what? 365.9 over 365. I just added those two numbers. Let's go to Calcutron and see what they say about this answer. Calculator. Do I have an exponential thing? Okay. So it's ln of 8 ln divided by parentheses 365 times ln, crap, and it did that chunk. Okay, so let me try that again. Sorry, I'm not used to this calculator. 8 ln divided by parentheses. Let's put another parentheses in there, right? Yeah. Parentheses 1 plus 0.9 divided by 365, and the parentheses on that inside, but then I want to take the log of that chunk, and then end the parentheses on that thing, and then multiply it by 365. What a nightmare. Well, I hope it ended the parentheses correctly. I don't think it did. Tricks. How do I get back in my memory? Well, anyways, put it in your calculator. I guess I got a little mini calculator I'll do. Hold on. Oh my god. ln of 8 divided by 5 times 1 plus 0.9 by 365 in parentheses on that. And logarithm and parentheses on the denominator. 2.31 is what my calculator is saying. So approximately to 3 decimals, 2.313. Let's see what they want. Yeah, 2.313. Okay, we'll leave it at there. If you got any problems, come see me during my office hours. I can always help. Okay, we'll see you next time.